Okay. Today, the mode of discussion today is actually kind of we are wrapping up about the discussion of Schottky junction with some piece of information. Okay? I'm going to give you some piece of information. Now it's your duty to collect, to understand those piece of information and try to check that whatever we have studied, whether it goes as per our knowledge, whatever we had earlier days. Okay, so that is it. So here it is kind of linking about your knowledge to this about our discussion. Okay, so let's the title. Okay, is it okay, title more on information? Okay. Um, what are these? Not copying. Students, just 1 minute again. I think. Can you send the Google group information? I think I have given the same group, but it's not allowing me to copy. I don't know why. Just drop the message to this Google group information to my email ID once more. Okay. Anyhow, so it's not allowing me to copy. That's all.
So you can visit the link by clicking.
Is it okay? Okay. So student, just check because I have just shared the folder which I'm going to about this discussion on this video lecture of this code. Just check if there is a problem or not later on after this class. Okay, so what happened? So last day, if you can remember that our discussion was like something, a very interesting thing. What is that? This is like if you have such kind of interface states, like let's draw the interface state first. Let's draw the interface state first, and this interface state concept we already have, so I don't think you will have a problem to understand it. Okay, so this is, can you remember, this is which we called phi m. This is actually BBI or QBBI because if it is energy, this is, can you remember, this is my grade 5n, right, friend? Okay, and the important part is that this is kind of what we have described. This type of what is the 5? Okay, so I'm sure you know what is called this one. So this is EG. Okay. So for this, what happened? Like, what is the 5n? So phi m minus chi. Chi means like This is not like that. So just have a look on our discussion last day and you'll understand. And this we are calling actually Schottky model. Or we can say is it actually called what is called ideal model, right? So that is also, let's check it. Ideal model. But what is important, but when people are trying to regenerate this data point from experiment, they found that the whatever 5n they are getting, 5n you can write experimental. So it is like 0.7 electron volt to like 0.8 or let me like 0.9 electron volt. And what is approximately, what is the reason for it? People have described this phenomena called there might be lots and lots of interface states are there. And these interface states actually has a peculiar nature. And what is this nature? So it is having something called the E0 neutral point, and these are the acceptor levels. This is the donor level. So that we have find out, right? And we have, and this is your band gap. While it's very easy to understand because, and we have defined these things quite nicely because for an example, like if your Fermi level over here, it is EF, that means you are actually uncovering this portion over E0. So that means you are generating negative charge across your surface or interface. Now, so it's not about our discussion on compound semiconductor. You'll have the same discussion about to understand about MOSFET, metal semiconductor like capacitor, and from the MOSFET measurement you can find out number of defect densities or number of interface states, which is called DIT, the interface states density, DIT. Just remember, interface states density. So you can calculate. Okay, that is quite states, and that DIT find out is actually basically from this theory. Who has developed this theory? The theory has been developed by Bardeen, Dr. Bardeen, who got Nobel Prize on this, for this development. And after that, you know, after that Intel has come out and Intel could produce lot of CMOS, okay, after this invention. It's a remarkable invention, okay. And then Intel came out and Intel now is dominating because of this invention. It's equally important in our compound semiconductor, it's equally important in the CMOS based industry also. Now find out, so we got nice idea, but there are two things which I am trying to discuss today. First thing, I'm just trying to draw what is called, you can understand. This is my interface states and it might have some silicon dioxide or some oxide layer, a lot of defects and everything. So which I am not drawing. What is important over here? What is 5n? So suppose this. So suppose you have a lot of interface states, like lot of interface states, and you know we just find out. Okay, this 5n if you have a lot of interface states, this 5n is actually, if you, I am not so sure, gamma, I think, gamma is equal to 1 by 1 plus qd. So if gamma is equal to 0, so this is infinity, so this is 1. So, okay. Just help me whether it is correct or not, but plus something, okay. So what is important, like if you have a surface over here, and so because of this, if you have a surface over there and surface that could not, like, see, getting ideal Schottky junction is practically impossible. Impossible. You'll have definitely have an interface states. So the moment interface states come, so you are actually seeing this the 5n relation with this continuity. Like 5n is a chi Eg minus phi 0. So what is important part is that here, like if you so you can understand what was the discussion last day, like 1 by 1 plus q dit, remember, okay, if you see. So if your density of interface states is very high, very high, so you will see this chi is equal to, okay, this is very high, suppose infinity. So 1 by infinity means 0. So I think I have made a mistake. So go back, check. Phi m minus chi is equal to gamma. Phi m minus chi is equal to chi. So yeah, so I think I have to redraw it, rewrite it. 5n phi m minus chi gamma Eg or something. So if you have a lot of interface states, like 10 to the power 10, 10 to the power 12 parts centimeter square, as you know, it's a surface phenomena. What will happen? Your 5n, you can say it is kind of proportional of Eg minus phi 0. So you can see, like Intel has tried for CMOS purpose. CMOS, Intel has achieved around 10 to the power 8, 10 to the power 9 per centimeter square interface state. See, 10 to the power 8, 10 to the power 9 per centimeter square. So that many interface states you are having, Intel could not reduce further. So tremendous. So whatever defect, whatever device you are seeing, it is having that many amount actually. Right, and it is like a huge, like I think you don't, whether you know or not, Intel has an open challenge program so for the device physicists. So if anyone who are like can reduce the interface state density down to 7 10 to the power 7 per centimeter square, so Intel are giving a 0.001% of the profit. I mean, like this is a kind of like they can give, they may give, because this is a huge challenge, because to reduce further 10 to the power 7 or down to 10 to the power 7 is very difficult. But there's a lot of open challenge are there. Like if anybody giving proposal of like reducing this many interface state, even one order is less, it's a, you can get lot of money. So a lot of industries are waiting to give you money to take this patent out. patent, because definitely you are going to give a patent, so they are going to buy the patent, see, huge amount, huge amount. Okay, so it's an open challenge. So now the thing is that why it is so, no, question is why it is so important, like what is happening, like if you reduce the one order, two order. So thing is that if you have a defect like 10 to the power 10 or 10 to the power 12 or 10 to the power 13 per centimeter square, it is as if that in your DIT is actually infinity. 10 to the power 12, 13 is infinity. If it is infinity amount, so you can see your 5n is your phi m, that is metal work function and electron affinity. This totally depends on the semiconductor. Though semiconductor band gap and the neutral point of your interface stage, right? That we have seen. And what, so that means if you have a defect, so you are going to have a 0.8, 0.9 electron volt of energy, like that 5n of around this much 0.8 or 0.9 electron volt means you have that many barriers, means to get ohmic contact out of this barrier is become a problem. Okay, right? So you'll always have a barrier depth, or you'll always have a like a huge contact resistance drop over contact resistance, high contact resistance. So you and you have a like loss of voltage against this contact resistance, right? So this is a problem. Okay. Now people are defining. So what I am defining today you have to see. So whatever we have derived, okay. So whatever we have derived, this is actually N-type semiconductor. We have found that N-type semiconductor, getting ohmic contact out of the N-type semiconductor is very difficult. Why? Or the contact resistance drop of N-type metal N-type semiconductor junction is very, very difficult. Why? We just now had a discussion, no? Because whatever the band diagram, everything I have shown, it is because of N-type semiconductor. Now, what you have to do, check this theory, check and find out 5 Vp, which for P-type semiconductor. Remember, this is your homework. Remember, whatever we have discussed and about a 5Vn, like for an example, like here, if this is 5Vn, so this is my 5Vp. It means like Eg is equal to 5Vn 5Vp. What it means? Like if your 5Vn is high, so 5Vp is low because your Eg is constant, right? For an example, like for 1.1 electron volt of silicon, your 5Vn, someone told me last day, is equal to 0.7 electron volt. So what would be your 5Vp? Around 0.3 electron volt, 0.3 or 0.4 electron volt. So that means the more you have a 5Vn, 5Vp is low. What is this indication is giving? Like for P-type semiconductor, you might. So for a particular condition, you might have a problem of getting ohmic contact for N-type semiconductor, N type of carriers. But you'll have easy contact for holes, which you need to verify. Which I'm not going to discuss, you need to verify. What I'm saying, like check and find out 5Vp for check and find out. For like for P-type semiconductor. So my statement is N-type semiconductor ohmic contact is very difficult. N-type semiconductor, what is the majority carriers is electrons. For electron, it is very difficult. Okay. Now, what happens if you have a p-type semiconductor of same amount of defects? Same amount of defects, p-type semiconductor, whether are you getting like huge amount of barrier height or not? So that you need to check it. So that is your homework. Third, which is very, very important, like what I felt like, which like if you go to SMG or Streetman Banerjee, they have calculated 4 different conditions. What is that? Phi m greater than phi s for p-type semiconductor. Phi s greater than phi m for p-type semiconductor. Sorry. One, two. You understand phi m greater than phi s for n-type semiconductor. Phi s greater than phi m for n-type semiconductor. So here you please find out what is the phi vn and phi vf and phi vp for ideal case. Why ideal case? Because non-ideal case for compound semiconductor is very easy. Why? Because we are not dealing any p-type semiconductor for compound semiconductor. Again, I'm telling, we are not dealing any p-type semiconductor for contact semiconductor, compound semiconductor. So we all are dealing n-type semiconductor for compound semiconductors, so one already we have got. Like for n-type semiconductor, ohmic contact is very difficult. Means for n-type semiconductor, we are getting always a high contact resistance, right? Now I have asked just for an example, like if suppose we are giving, okay. So this is actually our master kind of semiconductor. That means we are bound to take n-type semiconductor because it's having high mobility. Okay, but problem is that we are always getting a high contact resistance, which is not acceptable. So I need to find out a proper solution for that, which I am going to discuss. But for sake of understanding, so you can say like what is happening that if I have a lot of interface states, and in that case, what is happening? My phi BP means if you have a metal p-type semiconductor, can we have ohmic contact? You have to convince, you need to convince yourselves. In that case, getting ohmic contact for p-type semiconductor is not at all a problem. That is why for silicon, p-type silicon, you are going to get ohmic contact. You people always using aluminum. So why this combination? So this combination p-type semiconductor for silicon, you are always going to have is use aluminum. So you can ask like, see, I have a huge interface states. Then how can I get a ohmic contact for p-type semiconductor? That you need to convince if you follow the same step what we have discussed in last day. Okay, so that is actually your homework, which I am looking for from your side. Okay. Now, what is the solution of n-type semiconductor, which I'll discuss in a minute, but you need to check the metal p-type semiconductor contact and the phi BP value. You'll see the phi BP value, even if we have a plenty of interface states, it is very, very low. So getting ohmic contact for p-type semiconductor is very easy than getting ohmic contact for n-type semiconductor. Okay, so that. Okay, another homework which I have given you, because it is there in the SMZ book and Straitman Banerjee book, like they have discussed like different condition, and here you have to convince yourself that Suppose you assume that you don't have any kind of called interface test. Suppose if you don't have an interface test, then how we can get ohmic contact or rectifying contact out of this configuration? So phi m greater than phi s, a p-type semiconductor, whether it's a ohmic contact or rectifying contact. And if on both the cases you have to find out phi vn and phi pp. So that is your homework. Okay, you need to read little bit of books on it. Okay, so it's not that great. I mean, anybody can do it. The finally, actually, I'm giving you solution, and that solution you see is very trivial. Solution, as I promised, N-type semiconductor with metal, and we need ohmic contact or low contact resistance drop. How it is possible? So it is possible. How? Let's look at that part carefully. You come, so suppose, it's very easy to understand because you have already done this exercise. What? Okay, so this is my N-type semiconductor, right? Okay, now I should have drawn a little bit higher so that it's just for you to understand, huh? So that I have, it's not at all exercise. So what is 5N? So you have a 5N over here for, and you understand it's an N-type semiconductor. Okay, so 5M greater than 5S. So you have a 5N. And for this, you know, this is my depletion region, right? You already knew about this part, so nothing, it's not special for you. I mean, you already have done it. And let's assume this is my HD, depletion region, because you are getting a drop across the depletion region, correct? Right. Now, look at that. If you try to reduce your HD, can you reduce your HD? How to reduce your HD? Suppose you reduce your HD with this phenomena. Okay. But how to reduce your HD? So your HD is a that means if you increase your ND, doping concentration, your HD will decrease. What is the consequence of HD? Let's try to, so that means you are increasing your doping concentration. The moment you increase your doping concentration, you see. Okay. Accordingly, this will happen. Like if you increase your HD, if you increase your doping concentration, how it looks, that you are creating more and more carriers across your junction. So your thing would be more close to your Fermi level, correct? Just one. Hello. हाँ 10 मिनट लग गए. So this is the thing. Similarly, if you increase more doping, so what will happen? So I am not drawing EV, huh? So EV you can draw. I'm not drawing, that you can understand. So what will happen? So if you try to increase the doping concentration, so modified doping concentration, let me draw. Now you see earlier your 5VN is like that. But what you will be getting, there are two theory over there. One thing, this band, you see this part, you see this part is so small, it's so thin. Electron can tunnel through it. Instead of jumping from here to here, electron can tunnel through it. One theory is like that. So it's called the tunneling theory. Second thing is that what is your effective barrier height? In this case, what is your effective barrier height? So people are saying effective barrier height only this one. So your 5VN is actually reduced to this one. Actually, I don't know why people are saying it is a two theory, because I feel like it is the same theory, because effective barrier height actually reduced over there. So like this is my effective barrier height 5VN bar. And so that means electron can jump from here to here. I mean, like metal side to semiconductor side, aram se. There's no issue. So that is the thing. Like if you increase your doping concentration, your depletion layer width has decreased. So effective, your barrier width actually decreased. Where is the application? Look at this application. You know that application, but you never realize. When you try to fabricate any type of semiconductor MOSFET, you see people always do N++. Now you can ask why N++? Because this is the portion you are taking connection, metal connection. So this is a metal, and this is your N-type semiconductor. If it is not doped heavily, you never get an ohmic contact, a low contact resistance problem, low contact resistance. If it is not doped heavily, the moment you dope heavily, you see that there won't be any contact resistance across this junction. Remember, this is one of the reason that why you are putting like N++. Second reason is that you need to create a lot of electron tank, like electron field in the tank. Okay, so whenever you need, so this tank will supply electrons. So for this, you need to have a lot of carriers across this zone. So it fulfill both the case. But major thing is that it gives you, yes, it gives you ohmic contact, that is low resistance drop, low drop resistance. Okay, and that is to get these things people are doing N++, means higher doping. The moment you have a higher doping, your barrier height actually reduced over there. There is another concept, so that you please check that is that N-type semiconductor metal usually is very getting to get ohmic contact, but if you at all try to get it, you have to have N++. Then only you will get, or higher doping concentration. Another thing is that in interview question, it is very important. People always ask like a Fermi-level pinning. What is that? Pinning. It's very important question. And it's very favorite question. Those people who are doing little bit hardware, like who are actually fabricating a device. It may be sensor, it may be MOSFET. This Fermi-level pinning is very good concept. And what is that? And how you can understand Fermi-level pin, the Fermi-level halting situation. So it is like that. You have a lot of defects, okay, and okay. Let's draw this defect part. Oh, let's draw. You have EC and EV. Look at that. You have not contacted any metal from left side. There is no metal at all. You have a semiconductor surface, a lot of contacts over there. And what will happen? These contacts are these are the defects. these are very prone to take electrons or give out electrons. They have very electron affinity over there. Like so. Moreover that, what will happen? You have doped the semiconductor. Suppose if it is my E0, look at if it is my E0. Suppose you have doped the semiconductor at higher level, right? So let's give me another color, higher level. So it is my EF. So suppose it's a, because it is an N-type semiconductor, no? So let's look. Suppose this is my EF. The N-type semiconductor, no? You understand? It should have. That means I have doped the semiconductor in this level and E0 is there. So these are the like defect states. They want to have electron. They want to have electron because see, you have a semiconductor, you have a substrate. It doesn't mean say immediately grow metal to semiconductor contact. You have a you have first you go to the shop, you buy the semiconductor, then you deposit metal. So when you go to the shop, when you buy the semiconductor, suppose silicon or compound semiconductor, you have a lot of interface states. You have already doped it with EF. Means you have already doped the semiconductor. Suppose it's N-type doped. Now these are the green zone. It needs electron. Now from where it gets electron? They say like I can get electron from metal, yes, but metal is not there. Then where else? From where I can get the electron? Then semiconductor says, okay, so you need electron. So since you don't have any other option, so I have to give electron to you. That means now your semiconductor is giving electron to the interface across this interface. So what will happen? What will happen? You understand? I think you got a clue also that if this is my situation, you have, so this zone bend up look at that. Like I feel like it's a very beautiful physics, but okay, but it's a very dangerous physics because it's actually destructive phenomena. What will happen? There is no metal, still your band bending happened. There is no metal across your left side, but still you have a band bending, right? So that means your semiconductor already bended. Now, thing is that you got from the shop a bended semiconductor. Now, after that, whatever you do, whether you add or not, semiconductor doesn't bother because already equilibrium established over there. Whatever the electrons exchange happened already happened. So whether you add metal or anything, no electrons will go from your conduction band to your metal side. Already bending had happened. Already it is in equilibrium stage. Even if you add metal, nothing will happen. So that means this semiconductor is talking to your defects. It's supposed to talk to metal to get proper banding and everything, but due to high interface states, like 10 to the 15, 10 to the 16 per centimeter square, high interface state, your semiconductor is talking to your defect states. So whatever metal you add, nothing will happen. This is called like a Fermi-level pinning position. Since there is no electron exchange further from your conduction band to your metal, your Fermi level is kind of fixed. If there is a cross talking between metal to semiconductor, then only your Fermi level moving up and down, all these things are happening. So, but now it is already stopped over there. So whatever you do, semiconductor cannot see anything. Semiconductor cannot see anything about metal. Semiconductor cannot see metal. Semiconductor see only interface states. And interface state and semiconductor is saying that we have already shared the electron. Fine. Now in this case, if we even apply voltage, so the same thing will happen. So what you are expecting a current flow between your metal to semiconductor. So nothing will happen because semiconductor cannot see the metal, so there won't be any current flow. That means your Fermi level is pinned over here. This is called the great pinning effect. But theoretically, you can prove it in the following manner. Q ND into XD, right? So that is your total charge, depletion charge, and because of that your bending had happened, right? Is equal to Q PIT EF minus E0. Whom you have given this charge? I have given semiconductor has given this charge to that interface state. So the charge equilibrium has so like 100 number of electron has been provided by the semiconductor to the defects, right? So total 100 number actually has been exchanged. So that is 2. Now you see that if you have a DIT is very, very high. Your DIT is, this is actually kind of fixed. Now if you have a DIT is very, very high, EF minus E0 is very, very low, or it is kind of fixed. When this exchange of electrons will happen, that EF minus E0 kind of fixed. Either EF will, like whatever EF and E0 will be fixed means, so the distance between EF and E0 would be very, very low, right? That is what I am saying. Why it is very, very low? Because even EF minus E0 distance, it may be very small, but in these defects, in this small zone, plenty of defects are there which have taken the electrons, right? Because the number of defect density is very high, right? So in that case, you see that EF minus E0 is very low, or you can say that EF pinned to E0. EF Fermi-level pinned to E0. It's a very unexpected, it's exceptional phenomena. So what I'm saying, EF is pinned to E0. And this is called the Fermi-level pinning effect in terms of theory, in terms of expression. But ultimate thing is that it is talking to interface states, and interface states, since it is talking to interface, already bad bending can happen, everything is fixed. Since it cannot see the metal, whatever you do, since it cannot see the metal, so no charge exchange, and since there is no charge exchange, EF is actually kind of fixed over there. Okay. So I'm stopping over there, and this is kind of finish of the Schottky junction diode. There are few things I have to tell. Remember Richardson constant. Richardson constant, if you do all the exercise, it is kind of 120 by m star by m0. Look at that Schottky diode expression. So what was our discussion? Our discussion is that if you want to find out J0, we need to know this one, 5n by kt. We need to 5n. We need to know 5n, right? That was, then only you can calculate J0. Now still we have to calculate the J0. For this we need to know A star, e to the power 5n okay, Schottky diode minus 5n by A to T star. Okay. A star T square into A. Now the thing is that so now you see that all discussion happened towards the 5n, right? So A star means 120 by m star by m0. So how I got it? It's your homework. You please try to find out, and this convince yourself this is correct. into minus 5n. So suppose you assume that you have a lot of defects. If you have a lot of defects, so your silicon m star by m0 is around 0.67. Because if you know the effective mass, and suppose you have a plenty of your 5n. So what is your 5n? Eg minus 50. So suppose you have a DIT is actually, you just consider an ideal case where DIT is equal to infinity. If you consider DIT is equal to infinity, your 5n is equal to Eg minus 50. You put all the value back to J0, all these things to the J0 expression and find out a number for silicon. Similarly, you can do same thing for gallium arsenide also and try to find out the J0 value theoretically for a particular metal semiconductor composition, and you will get the value. Now you can compare both the J0, which one is actually less, which reverse saturation current is less. So that is also like your homework for the yeah. So I have to find out, yeah. So fourth problem, you have to find out what is the value. That is what all discussion has started. No, so J0 for silicon and gallium. So J0 is a metal semiconductor for reverse saturation current. And in this case, what we have assumed, DIT is equal to high. DIT is equal to high. So please do it and come back tomorrow, because it's very important that you do this exercise, because tomorrow we are going to start MESFET on this discussion, on these things. Okay. Okay. So
Sir, we haven't got any mail regarding your videos.
I think I have shared this video, no? Can you please change 1 minute? It is showing it is shared. Okay, one thing, 1 minute. If you don't get, no problem. Let me. Okay, it's not possible. So in that case, there is only one solution is with me. So I have to Ankit, then Rajashri, Harshit, Sharat, Bhuvan, Akshay, Apurva. So I'll share today itself with individual Gmail ID. I think I have. Oh, I hope everyone is. I am having all this. Okay, fine. I'm stopping over here.